Good morning, student. Today we are going to study about Bayer's strain theory and the orbital picture of angle strain. So Bayer's strain theory is nothing but angle strain theory that was proposed by the scientist Baeyer, and it is applicable for all the cycloalkanes. Now what he proposed or postulated is that any deviation of bond angles from the normal tetrahedral value would impose a condition of internal strain on the ring. So what he said is, if there is a cycloalkane, if you have a ring structure and if there is a deviation from the normal tetrahedral value of the bond angles. Now we know that the tetrahedral bond angle is 109 degree 28 inches. All right, so he proposed that any deviation from this value would result in the strain on the ring. All right, so the bond angle that is for tetrahedral geometry is this, that I have already told you, 109 degree 28 inch. Okay, now what he proposed is that in order to obtain the maximum overlap of the atomic orbital, the bond angle should be 109 degree 28 inches. Okay, if you could see, this is our sp3 hybridized orbitals, and the overlap is maximum when the overlap is head-on overlap, and this only happens in case of tetrahedral structure. When you have a perfectly tetrahedral structure, for example in case of methane, you have this kind of overlap. So what he suggested, if there is any deviation from this, then the overlap will not be optimum, and if the overlap is not optimum, then there will be a angle strain. This is the sideway overlap I have shown you. Okay, now what he said, if the overlap is effective, then the bond strength will be maximum and your molecule will be stable. All right, or in other words, you can say the reactivity will be lesser. Now if you could see, I have taken the example of cyclopropane. This is the cyclopropane ring. The bond angle is 60 degree, and if you see the deviation, this is tetrahedral angle, it is 109, around 109 degree, and the deviation is around 49 degree. So the deviation is very large. So in case of cyclopropane, you get some ring opening reaction at the normal temperature. For example, if you react the cyclopropane with the HBr, you will get something CH3 CH2 CH2Br, product like this, brominated product, and the ring will be open. This ring will be open and a substituted product will be obtained. So this kind of reaction are shown by cyclopropane easily at room temperature. This is because the overlap is not optimum, so the bond strength is less and hence the stability is less, resulting in the higher reactivity of cyclopropane. Now what was the exact wording of Baeyer? He proposed any deviation of bond angle from the ideal bond angle value, that is 109 degree 28 inches, will produce a strain in the molecule. Now if the deviation is higher will be the instability. जितनी ज़्यादा deviation होगी उतनी ज़्यादा आपकी cycloalkanes की instability होगी. So I have taken 4 cycloalkanes here: cyclopropane, cyclobutane, cyclopentane, cyclohexane. Each of them having angles 60 degree, 90 degree, 108 degree and 120 degree respectively. Now if you see the deviation, in case of cyclopropane it is around 49 degree, in case of cyclobutane it is 19 degree, In case of cyclopentane, it is 1 degree. In case of cyclohexane, it is around 11 degree. In case of cyclohexane, the deviation is negative. Now, we already have said this plenty of time. Deviation of bond angle from the ideal value produces strain in the ring. Higher strain produces increased reactivity and increased heat of combustion. If we look at the values, if we look at the deviation, we can simply say, if we compare these three things, cyclopropane, cyclobutane and cyclopentane, we can say that our cyclopentane is most stable, after that cyclobutane, after that cyclopropane. So the stability order, we can write it is something like this. This is the order of stability. And when you see the reactivity, when you see the other properties shown by these compound, you will find that this order is correct. This order is correct. The stability order for these three cycloalkanes is correct. But when you compare the cyclohexane and cyclopentane, it suggests that your cyclopentane is more stable than cyclohexane. Okay, so that means your cyclohexane should be more reactive as compared to cyclopentane, but this statement is actually incorrect. You must have studied in your school also that cyclohexane 6-membered ring is more stable than the 5-membered ring. This you must have studied. And if you see the reactions, if you compare the reactions of both of these compounds, you will find that cyclopentane is highly reactive as compared to cyclohexane. So that on basis of that, we can say that this statement is incorrect. This could be a limitations of Baeyer's strain theory. This table gives us the cycloalkanes and their respective deviation that we have already discussed. This order we have discussed. This is a correct statement. The stability order of is in the way cyclopentane is more stable, then cyclobutane, then cyclopropane. This is the correct statement. The incorrect statement that the Bayer strain theory suggested was cyclopentane is much more stable than cyclohexane. This is incorrect, and this was found by studying the reactivity of both of these compounds. Okay, so we now moving on to the limitation of BST theory. The very first thing that Bayer strain theory assumed was that all the cycloalkanes are planar. They assumed that all the compounds cycloalkanes are planar. So this assumption of theirs resulting in the wrong explanation, because Bayer assumed that cyclohexane is a planar compound as well as cyclopentane, and on basis of that he explained the order of stability, but this assumption in itself was incorrect. The higher rings, the rings like cyclohexane, cycloheptane, cyclooctane, all of these rings do not exist in the planar form, but they exist in a puckered form. Hence, they convert their angle. For example, in cyclohexane, we have seen that the bond angle is 120 degree, but that is not true. In actual, it has a bond angle of 109 degree 28 inches. This is the correct bond angle of cyclohexane because it occurs in the puckered form. It exists in a conformation like this, chair conformation, and because of this puckered form, the bond angle changes from 120 degree to 109, giving it the most stable structure. So we have to write down the limitations. We can say the Bayer's strain theory was not able to explain the effect of angle strain in larger ring system. When we discuss rings like cyclohexane, heptane, octane, in those cases the angle strain could not be explained. Now, according to Bayers, cyclopentane should be much stable than cyclohexane, but that is practically not true. Practically, cyclohexane is much more stable than the cyclopentane. And third thing, Bayer suggested that very large ring systems are not possible because they will have very high negative strain and thus cannot exist in nature. But this was also found incorrect. The higher ring systems exist and they are much more stable, and the stability is due to the puckered form in which these larger ring system exist instead of the planar structures. So this is it for the Bayer strain theory and our orbital picture of angle strain.